I want you to take a second and just recall a highly specific but universally frustrating experience.
Oh, I think we all have one of those.
Right. So you are perfectly crafting a message, or maybe you're filling out one of those extensive multi-step enterprise forms.
The ones that seem to take the better part of an hour to get through.
Exactly. You've got the formatting and the data just right. You confidently move your cursor, you hit save, and then,
You're just watching sheer horror.
yeah, the loading spinner just freezes. The console throws some massive error, and all your hard work completely vanishes into the digital void.
It's awful.
And the culprit is almost always the same, you know? Your internet connection dropped for exactly 3 seconds right during the handshake.
It is a uniquely modern kind of heartbreak. I mean, especially considering how fault-tolerant the rest of our digital ecosystem has become.
Right, like everything else works so well.
Yeah, but this underlying technology just pulling the rug out from under you, it isn't just an annoyance. In professional environments, think like healthcare applications or financial dashboards,
Oh, wow, yeah.
that ephemeral data loss,
Yeah.
it can have severe consequences.
Well, we are taking a deep dive today into an article that addresses this exact vulnerability in modern web architecture.
It's a fantastic piece.
It really is. It's called The Secret Life of JavaScript, the Background Sync by Aaron Rose, and it was published on the tech-reader blog.
Highly recommend checking it out.
Definitely. And our mission for this deep dive is to explore the specific architectural patterns that solve this problem. We want to uncover how modern development can transform these fragile network-dependent applications into robust, offline writable experiences.
It's a huge shift in how we think about the web.
It is. Okay, let's unpack this. So the way the author frames this technical problem, it totally bypasses the usual dry documentation style, right?
Yeah, entirely.
Yeah.
He sets the narrative with these two characters, Margaret, who's a senior software engineer, and Timothy, her junior colleague.
And they're operating out of this grand Victorian library in London.
Which is such a great detail. The setting itself serves as a metaphor.
Yeah.
You know?
How so?
Well, a physical library represents permanence, right? Archiving, craftsmanship. And those are values that stand in stark contrast to the brittle, transient state of a standard web form that relies on a fluctuating Wi-Fi signal.
Right, that setting creates a perfect juxtaposition for the code quality they're aiming for.
Exactly.
So in this environment, Timothy finds himself dealing with a pretty catastrophic failure in an otherwise flawless system.
Yeah, he had just finished implementing this highly resilient offline architecture for reading data.
Using the scale while revalidate pattern, right?
Spot on. So users could browse the application's dashboard perfectly while disconnected. It was great.
But then he goes to test the update profile form.
Right. He toggles his network connection to offline, types out this lengthy biography, and clicks save.
And it triggers a complete system collapse.
Yeah, the DevTools console immediately threw this angry red text, typer failed to fetch.
Oh.
The application crashed, and the uncommitted data was just completely wiped from the DOM.
Which is just, I mean, from a user experience perspective, that represents a massive trust deficit.
Huge. Because building a seamless offline reading experience, it sets a baseline expectation for the user.
Right. If I can navigate smoothly without a connection, I assume the whole app works offline.
Precisely. So allowing them to input data only to vaporize it upon submission, it basically punishes the user for trusting your interface.
It's like handing a carefully written letter to a mail carrier, right?
Okay, I like this.
And their strict protocol dictates that if the post office door happens to be locked at that exact millisecond, they are required to immediately shred your letter.
Rather than just holding on to it. Yes,
Instead of just putting it in their pocket. It's an incredibly unforgiving system.
It really is. So Margaret takes one look at the console error and diagnoses the root cause immediately.
She says Timothy has hit the hard limit of the cache API.
Which brings us to the core technical limitation of traditional caching strategies.
Right, because the stale while revalidate pattern he used is great for GET requests.
Exceptionally good. It intercepts the request, serves the stale asset from the cache, and silently updates it in the background.
But the Patch API categorically refuses to cache a POST request, or any data mutation for that matter.
Yeah, it just won't do it.
Let me push back on this architecture on behalf of the listener for a second.
Sure, go for it.
Because developers build retry logic into applications all the time, right?
They do, yeah.
So if the browser is smart enough to intercept a network request and it can cache thousands of static assets, why is the cache API intentionally designed to fail on a standard fetch command that has a data payload?
That's the million-dollar question.
Why can't the browser natively pause that POST request until the network stabilizes?
What's fascinating here is the concept of idempotency.
Idempotency. Okay, break that down for us.
So the browser has to assume a defensive posture when dealing with data mutations. A get-DEET request is idempotent,
Meaning?
meaning you can request the same image or the same JSON payload 10,000 times without changing the state of the database.
Right, it's just reading data.
Exactly.
Mm-hmm.
But a post request, a data mutation, is not idempotent.
Oh, okay.
If the browser were to natively pause and automatically retry a failed POST request behind the scenes, it has no way of knowing the intent of that payload.
Meaning the browser could accidentally submit a payment twice?
Yes, or duplicate a database entry simply because a shaky connection caused the first attempt to drop its response packet.
Oh, so it thinks it failed, sends it again, and suddenly you've bought 2 plane tickets instead of 1.
Precisely the danger. The browser forces the developer to handle mutations manually to prevent silent data corruption.
That makes total sense.
Furthermore, a fetch request isn't some serializable object you can just store on disk. It is an active, executing instruction on the main thread.
Right, so the user interface in Timothy's initial build is far too tightly coupled to the network state.
Exactly. When the user clicks Save, the UI demands an immediate, synchronous success or failure from the server.
And if the network isn't there to answer, the active instruction dies.
And the data held in memory dies right along with it.
That structural dependency is the real issue. The mail carrier literally cannot hold the letter because the system doesn't provide them with a pocket.
I love that analogy, yes.
So to fix this, Margaret moves to the whiteboard and outlines a decoupled architecture. She divides the application's responsibilities into 2 separate domains.
Right, the main thread and the service worker.
Decoupling the user interface from the network is the foundational step here.
It really is. Margaret's solution begins with intercepting the save action entirely.
So instead of allowing the app to blindly attempt a network request that might fail,
The payload is immediately serialized and written to IndexedDB.
okay, for the listener, IndexedDB serves as the browser's persistent local transactional database.
Yeah, it's built right in.
Here's where it gets really interesting. Instead of the UI attempting to run directly to the post office and facing that shredder protocol we talked about, it takes the document and drops it into a secure, permanent outbox sitting right on your own desk.
That's exactly what's happening. The data is secured locally before the network is even consulted.
And that architectural shift changes the entire failure surface of the application, doesn't it?
Completely. By writing to IndexedDB on the main thread first, the application instantly secures the user's input.
The risk of data evaporation just drops to 0.
Because the data is safely persisted to disk, you completely eliminate the network from the initial save interaction.
But wait, securing the data locally has to introduce a new set of complex edge cases?
Oh, absolutely.
Like, what happens if the user is offline, they get frustrated, and they aggressively clear their browser cache or local storage before the connection comes back?
Yeah, that's a nightmare scenario.
Doesn't relying on a local database expose the app to user-induced data loss?
That is a critical vulnerability developers really have to account for, because IndexedDB operates under the browser's storage quota policies.
Meaning if a device is critically low on disk space.
Or if the user manually wipes their site data, yeah, that queue can be destroyed.
So how do they mitigate that?
Well, robust applications utilize the Storage Manager API to request persistent storage.
Oh, I've seen that prompt sometime.
Right. If the user grants permission, the browser treats that IndexedDB instance as highly durable. It will be cleared automatically during routine garbage collection.
Okay, but what if they go into settings and manually wipe it?
A manual, intentional wipe by the user will always win. The local queue is incredibly secure, but it isn't completely invincible.
Okay, so assuming the data remains secure in IndexedDB, the user still ultimately wants their profile updated on the server, not just saved as a local draft.
Right, securing the outbox is only half the battle.
We still need a delivery mechanism. And this is where the second box on Margaret's whiteboard comes into play.
The background sync API.
Which operates entirely within the service worker.
Exactly. And the service worker, it acts as an independent background process. It's completely detached from the lifecycle of the web page itself.
So once the main thread successfully writes the payload to IndexedDB, it doesn't even try to send it.
Nope. Instead, it registers a sync event with the service worker.
And what does that do?
The background sync API essentially acts as this highly intelligent patient event listener. It just sits there monitoring the operating system's network state.
So if you're offline on the subway, the API registers the event and just goes dormant.
Yep, it waits. And the moment the operating system detects a restored Wi-Fi or cellular connection, the background sync API fires the event.
Which wakes up the service worker.
Exactly. The service worker wakes up, queries IndexedDB, retrieves that serialized payload, and executes the fetch request to the server.
And it handles all of this invisibly.
Totally invisibly. The complexity of managing retries, checking connectivity, executing the network request, all of that is offloaded from the main thread to a background agent.
Okay, this raises a massive performance consideration, though.
I know exactly where you're going with this.
If we have service workers constantly running in the background, just waiting to fire sync events, what is the impact on battery life? What about system memory?
It's a huge concern.
Right. Are we creating these zombie processes that just drain a mobile device's resources while waiting for a signal?
Browser vendors anticipated that exact issue. That's why the implementation of event.waitUntil is so tightly regulated.
Okay, how does that work?
The service worker isn't actually spinning in the background consuming CPU cycles while offline. It goes completely dormant.
Oh, so it's not actually running.
Right. The browser hooks into the host operating system's native network APIs.
Ah.
When the OS broadcasts that a connection has been established, the browser wakes the service worker up just long enough to execute the promise inside event.waitUntil.
And once it's done?
Once the promise resolves or rejects, the service worker is immediately spun back down. It's incredibly resource efficient.
That's brilliant. And Aaron Rose specifically notes a detail in the source material that, to me, fundamentally shifts how we view web applications.
Yes.
Wait, so to be clear for the listener, this entire background sync process works even if the user has fully navigated away from the page or even closed the browser tab entirely.
Yes. You can hit save, see you're disconnected, close the laptop in frustration, and the browser will autonomously fulfill the request hours later when you open it at a coffee shop.
That is wild.
Margaret refers to this as guaranteed delivery.
Guaranteed delivery, I love that.
By wrapping the fetch request in event, wait until, the API monitors the state of the promise.
So what if the background fetch fails? Like, say, the coffee shop Wi-Fi requires a captive portal login before you actually get internet.
Then the promise rejects. And the background sync API applies an exponential back-off algorithm.
So it automatically schedules subsequent retries without just hammering the network over and over.
Exactly.
Okay, guaranteed delivery is powerful, but it inevitably leads us to the problem of conflict resolution.
Oh, yeah. The classic sync problem.
Right. Let's say I update my profile offline on my laptop, and the payload sits in IndexedDB waiting for a sync event.
Okay.
In the meantime, I open my phone, connect to cellular data, and update my profile with entirely different text.
This happens all the time.
When my laptop finally connects, the background sync API is going to fire and potentially overwrite the newer data from my phone, right? How does the architecture handle that?
That is the exact reason idempotency and manual payload handling are required.
Yeah.
Because the background sync API only guarantees delivery.
Right.
It does not guarantee state synchronization.
Ah.
Developers have to build conflict resolution directly into the API endpoint. Usually this involves attaching a timestamp or maybe a specific version hash to the payload when it's written to IndexedDB.
So when the background sync eventually posts to the server,
The server compares the payload's timestamp against the current database record.
and if the server detects a newer entry, it can just reject the background sync.
Or it can utilize a conflict-free replicated data type, a CRDT,
Yeah.
to intelligently merge the text.
It pushes all that complexity to the backend, ensuring the client side remains focused solely on guaranteed transmission.
Exactly. Keep the client simple. Let the server handle the merge logic.
There is also a major security caveat that Margaret highlights during this implementation.
Yes, this is crucial.
Because the background sync API possesses the ability to wake up autonomously, execute code, and transmit data without any direct user interaction. Browsers enforce a strict HTTPS requirement.
The security implications of a compromised background agent are just massive.
Right. I mean, if an application were allowed to register a background sync over an unencrypted HTTP connection,
A man-in-the-middle attack could easily inject malicious code into the service worker.
and that code could theoretically lay dormant and quietly exfiltrate local data anytime the device connects to a network.
It's a terrifying thought. By enforcing HTTPS, the browser guarantees the cryptographic integrity of the service worker script.
So you know that the autonomous agent executing in the background is exactly the code the developer originally deployed.
Yes, no tampering allowed.
So with the architecture fully mapped out, Timothy implements all the changes.
He modifies the main thread to intercept the form submission, serialize the data, and write it to IndexedDB.
He then configures the service worker to listen for the sync event, retrieve the data, and handle the background fetch.
And then comes the big test.
He goes back to his DevTools, simulates an offline connection, types out his 3-paragraph test biography, and hits save.
And the difference in the user experience is just night and day.
The UI instantly flashes a success notification. There are no console errors, no type error warnings, and absolutely no freezing.
So smooth.
He completely closes the browser tab, toggles his system Wi-Fi back on, and invisibly in the background, the browser silently orchestrates the delivery.
It wakes the service worker, pulls the data from the outbox, and successfully posts it to the server.
The application handles the hostile network environment with total grace. It protects the user's input by shifting the burden of network management away from the fragile main thread.
And handing it to a resilient asynchronous system.
So what does this all mean for you, the listener? Whether you're building these applications or simply using them daily, this invisible background choreography is the defining line between software that feels broken and untrustworthy and software that feels native and magical.
That's a great way to put it.
When you are writing an email on a plane without Wi-Fi, hitting send and trusting that it will leave your outbox the second you land, this decoupled IndexedDB to service worker pipeline is the exact mechanism enabling that trust.
If we connect this to the bigger picture, Margaret summarizes the shift perfectly. It moves the web from an offline readable document viewer to a completely offline writable application platform.
It's a huge evolution.
Historically, treating the web as a remote library meant your access to the tools was entirely contingent on your connection to the building.
Right.
But by utilizing persistent local storage and background APIs, the web browser transforms into a fully capable local client.
It respects the user's time and data enough to decouple the active creation from the active transmission.
It effectively removes the anxiety of the save button.
It really does. We started this deep dive exploring the nightmare of the evaporating form, the catastrophic failure of relying on a real-time network handshake for data integrity.
Which highlighted the fundamental flaw of treating non-idempotent actions, like data mutations, with the same caching strategies we use for static assets.
And through Margaret and Timothy's architectural overhaul, we saw the definitive solution. By intercepting the data and persisting it to IndexedDB, we create an unbreakable local queue.
And by utilizing the background sync API within a secure service worker, we leverage the operating system to guarantee delivery.
Managing retries and network states completely invisible to the user, it represents a masterclass in resilient software design.
It definitely demands more upfront engineering, particularly regarding conflict resolution and cache management, but the return on investment regarding user trust is immeasurable.
It really is. Which leaves us with a rather profound concept to consider.
Oh, I'm ready.
If our web browsers are now fully equipped to act as autonomous agents, patiently queuing our tasks, monitoring system states, and executing our intentions long after we have closed the tab and walked away, what does that mean for our traditional understanding of when a digital interaction actually ends?
That's a fascinating point. The boundary between active use and background execution is completely dissolving.
It truly is. Thank you for joining us on this deep dive. Stay curious and keep exploring the invisible architecture of the digital world around you.